Alright, so now that we've done derivatives with implicit differentiation and also derivatives of inverse functions, we're going to combine them and find derivatives of inverse trig functions. And just as a quick reminder, inverse trig are functions like sine to the negative 1 of x or arc secant x. We use either notation. You'll see the typical inverse notation, and you'll also see an arc in front of the word, and both of them are referring to the inverse function. And inverse trig, if you remember, was dealing with the where on the unit circle, so you would have like inverse sine of root 2 over 2, and it's asking the question where on the unit circle is the sine of an angle root 2 over 2. Regular trig answers what, like what is sine of pi over 2, and inverse tells us, or asks us where on the unit circle these things happen. Alright, so for our first example, we're going to look at the most basic. So suppose y equals inverse sine of x. Find the derivative of y with respect to x using implicit differentiation. So if y equals the inverse sine of x, then we can simply take the sine of both sides to undo that inverse. So we would get sine of y equals, and then if you take sine of an inverse of that same function, that's how we undo it. So these two things undo each other, and it just leaves us with an x. Alright, so we found the inverse, and now we're going to try to differentiate both sides. Alright, so if we remember, the derivative of sine is simply cosine of the function, and we're using the chain rule here, so that was the derivative of the outside function, and now we'll multiply by the derivative of the inside function, or dy dx. And then the derivative of x is simply 1. And so if we solve for dy dx, we'll get 1 over cosine y. Now this is not our final answer. To get our final answer, we're actually going to do a little bit of triangle trig. And with right triangle trig, we have to remember our SOHCAHTOA in order to get what we're looking for in our answer. Alright, so I have a sketch of a right triangle. In our particular setup, I'm going to use this one right here. Sine of y equals x. Okay, so if sine of y equals x, if you remember, sine is this one right here, so it's opposite over hypotenuse. And I don't really see a denominator here, so I'm going to assume it's over 1, since usually trig deals with the unit circle. So for angle y, we're saying that the opposite of the angle is going to be labeled x, and that the hypotenuse will be labeled 1. Okay, so if you do some Pythagorean theorem here, then we're going to get that this remaining side that we don't know, if we express it in terms of 1 and x, is simply 1 squared minus x squared, and then we would take the square root of it to get the length of that side. And so now that we have this information, we can actually figure out what cosine of y is. Okay, and if we remember, cosine of y is dealing with adjacent over hypotenuse. And so according to our setup, adjacent of the angle is this expression here over our hypotenuse. And so now we can substitute this value, which of course we can just drop the divide by 1. We can come substitute that in over here. And so we're going to have dy dx equals 1 over the square root of 1 minus x squared. Therefore, the derivative of the inverse of sine is going to give us 1 over square root of 1 minus x squared. And that's our first inverse trig derivative. Okay, so the next one we're going to look at is arc secant x. So suppose y equals arc secant x, find dy dx using implicit differentiation. Alright, so y equals the inverse secant of x. And so similarly to the previous problem, we're just going to take secant on both sides. to find the inverse of that inverse. Isn't that fun? And again, similarly to the previous problem, we're going to set up a right triangle here. So we're still going to have it with respect to angle y, simply because that's what we're given. And secant is a little bit harder to remember, but let's think about it. Secant is the reciprocal of cosine. And cosine is adjacent over hypotenuse. So if we switch that, we'll get secant, which must be hypotenuse over adjacent. And again, it's just an x, so we're going to assume that denominator is 1. So we're going to come over here, we're going to label our triangle. So the hypotenuse is x in this particular setup, and the adjacent side is a length of 1. So again, if we do Pythagorean theorem, this side that's remaining that we don't know with respect to x and 1 would be the hypotenuse squared minus the other leg squared, and then we would square root it to find the actual length. And now we'll derive our setup implicitly. So the derivative of secant is secant tangent, and don't forget the chain rule here, so times dy dx. Derivative of x is just 1, so in this case we're going to get that dy dx equals 1 over secant y tangent y. So I already know what secant is, that's what we started with. Secant y is just x. So I can go ahead and set that part up. Dy dx equals 1 over x, and then I need to now use my triangle up here to find out the relationship of tangent. So tangent, if we remember, is going to be opposite over adjacent. That's what we're thinking here. So opposite the angle is this root of x squared minus 1, and adjacent is 1. So again, when we come plug this in, we drop that denominator since it's just a 1, and we're going to get times the radical of x squared minus 1. Now the one thing that's slightly different with this derivative than all the other ones we're going to end up doing is all the other ones are guaranteed to give us a positive value no matter what our x is, because we're squaring and square rooting a lot. However, this particular derivative has an x by itself out front, and if you look at the inverse secant graph, what you'll see is it always has a positive slope. Alright, so here's the graph of inverse of secant, and you'll notice no matter which side we're on, the slope is always increasing or positive. So because of that, when we're working with this derivative, we have to make sure we always get a positive slope answer, so we actually have an absolute value around this x in the derivative. Alright, so the derivative of the inverse secant function is going to be 1 over the absolute value of x times the square root of x squared minus 1. So there's our second rule we have now derived. We have one more to go. So the last one we're going to look at and derive ourselves is the inverse tangent function. Alright, so if y equals the inverse tangent function, we can simply take the tangent of both sides to get the inverse of that inverse. Alright, and then again for each of these I just set up a right triangle. So tangent is opposite over adjacent, so we're going to have our angle y, the opposite of that will be x, the adjacent of that will be 1, therefore the hypotenuse will be the sides squared. Oh, I don't really need to write 1 squared. The sum of the sides squared, and then we take the square root of that to get the actual length of the hypotenuse side. And now we're going to derive implicitly, so if we remember the derivative of tangent, we get secant squared y times dy dx equals 1. So dy dx equals 1 over secant squared y. Now looking at our triangle over here, secant, I'm going to find cosine first and then just find the reciprocal, that's easier for me. So cosine is opposite over no it's not, it's adjacent over hypotenuse. So that would be 1 over the square root of 1 plus x squared. And since we're now using secant, we're just going to flip that. since they are reciprocal functions. And so when I come over here and plug this in, we're going to get dy dx equals 1 over, and then again I'm just going to drop that denominator, so I'm putting this radical inside. So square root of 1 plus x squared, and it's getting squared since it is secant squared y. And so the derivative of tangent actually doesn't have a square root, but we know it's still going to be positive because it's an x squared. And there we are. So when we derive inverse tangent functions, we get 1 over 1 plus x squared. Alright, so that's all you really need to know in order to know all 6 of your inverse trig derivatives. Alright, so here are the 3 we just did. The derivative of inverse sine was 1 over the square root of 1 minus x squared. Secant was similar, but kind of rearranged. So it had a radical with x squared minus 1, and then it's the one that also had that absolute value of x in the denominator. Let me squish that in there. And then tangent was the one that didn't have any roots at all. And the reason you only really need to know how to derive these 3 is because similar to derivatives of regular trig functions, the co-functions are just the negative of that derivative. Okay? Except this time it's literally just the negative of the same thing. So the derivative of the inverse of cosine x is simply negative the derivative of our inverse of sine. So we typically, I just write the negative in the numerator. It really doesn't matter where you put it. For secant, let's see, that would be cosecant, and he's just the negative. And then for cotangent, again, just the negative of tangents, inverse tangents derivative. And there are 6 inverse trig functions. Now there are a couple things to remember. Don't forget the chain rule. Okay, this one's very easy to overlook the chain rule with. And then just remember that inverse, what's a weird I? Inverse sine of x is the same function as arc sine. People get afraid of the arc ones. I don't know why. I think they're easier to write, but they mean the same thing, just the inverse function of sine. Alright, so now we're going to do a couple quick examples of actually using these. And for each of our examples, you're simply going to find the derivative. So for our first one, we're going to find the derivative of arc secant of 2x. Alright, so f prime of x would be, and then if we remember, this is the one that had the absolute value. So we're going to have 1 over the absolute value of x, or whatever this is. So in all of our examples, we just had a plain x without any coefficients or anything else. But it's whatever's in the actual function, in the derivative, or the function itself, the inside function. So here I'm going to have absolute value of 2x, and the square root of that same inside function squared minus 1. Okay, that's step 1. Step 2, right, we just found the derivative of the outside function. Now we find the derivative of the inside function using our chain rule. So the derivative of 2x is simply times the 2. Alright, luckily that 2 will cancel out with the 1 in the denominator. And that's really the most we can simplify here, so we'll just end up with the fraction 1 over the square root of x times the square root of 4x squared minus 1. Done. Again, just watch out for that chain rule step. That's the one that's super easy to forget with these. For our second example, we're going to look at the function square root of inverse sine of x. So this is one I would definitely rewrite first, since we're going to be using the chain rule here. So the inverse sine is the inside function, and the outside function is that square root, or power of 1/2. So when we find the derivative, we're going to take the derivative of the outside function first, leave the inside function, and that will become a power of negative 1/2, times the derivative of our inside function, which is going to be 1 over the square root of 1 minus x squared. And it's just an x squared here because we were just taking the inverse sine of x. Now, if this weren't just an x, if this had been a 2x like the problem before, we would still have one more chain to do, but in this case we're good to go. So now let's try to clean this up. It's going to have a fraction of some sort. I see some negative exponents as well. So first I'm just going to clean up the first piece. So it has a 2 in the denominator, a 1 on top, and since this is raised to a negative power, that's also going to go in the denominator. And I'm just going to change it back into a radical, and we're multiplying it by this one over here. So really the only thing we can do to simplify this is kind of combine the radicals into one giant denominator. So when we multiply things under a square root, we can multiply them together under one giant square root, but just keep them in parentheses. Okay, so that times 1 minus x squared, and that would be as far as we could go with this one. Alright, and for number 3, we're going to do y equals 1 over the inverse tangent of x. Oop, there we go. So that means we can rewrite this one as well before we get going as just having a negative 1 power. And this is where math gets really confusing for a lot of people because we have two different things going on here. This negative 1 is just notation, right? So this is a problem where it would really honestly help me if instead I had written arctan, because that negative 1 is just notation of an inverse function. This negative 1 actually means a power of negative 1. So they're two different things. So if it helps you, I'm just going to rewrite it with the arc just so I don't get confused here about what's a power and what's notation. Alright, so now I'm going to do the derivative using the chain rule. So negative 1 comes down, multiplies by arc tan x, becomes power of negative 2. Then I multiply by the derivative of the inverse tangent function, so 1 over 1 plus x squared. And again, not much to clean up here. It's just got a negative exponent, so we're going to put it in the denominator and put it all together in one giant fraction. So I'm going to get a negative 1 on top, and I'm going to get arc tangent x squared times 1 plus x squared. I'm going to have to make my line a little longer. Alright, and that's really as much as we can do again. These don't really have a lot to simplify most of the time. Alright, our final example will be y equals x arc cosine of x squared. Alright, and so again with trig, be careful because it looks like one giant thing, but we're really doing the product rule here. We have an x, then we have the inverse cosine function. And then within the product rule, we'll also be doing the chain rule because of the x squared. So here we go. dy dx equals first times derivative of the last. So the derivative of cosine, remember he's just the negative of the sine one, and that's the square root of 1 minus your x, whatever it may be. In this case, our x is actually an x squared, plus last times derivative of the first. Okay, so let's put it all together. And this is where you ask yourself, did I just make the mistake I told you guys to watch out for? So hopefully you can see where the problem is, right? Yeah, I was just making sure you guys were paying attention, right? Totally. So when I take the derivative here, I even said it, this is going to require the chain rule. So we did the first times the derivative of the last, but the derivative of the last isn't done, right? Because it's not just an x here. So we really need a times 2x. See, this is how easy it is to forget. As part of that derivative. Gotta do the chain rule. Now let's try to put it all together. So in the first term, we're getting a negative 2x squared on the top over that square root in the denominator, and that would really be x to the fourth, and then plus arc cosine of x squared. And you can make this look prettier, but I feel like this is all we're going to do today. And that concludes our lesson on the inverse trig function derivatives.